Okay, in this video we're looking at vehicle safety. Pause for a moment, have a go at the starter, and then we'll carry on. Okay, so the starter question asks, a cannon of mass 150 kilograms fires a ball of 2 kilograms. The ball travels with a velocity of 10 meters per second. What is the recoil velocity of the cannon? So we're going to use the principle of conservation of momentum from last lesson to begin with. So for that we need to know what the momentum is before the explosion. And before the cannon is fired, both the cannon and the ball have 0 kilograms meters per second of momentum. Now, the principle of conservation of momentum tells us that if it starts with 0 kilogram meters per second, then at the end it's also got to have 0 kilogram meters per second overall. So we've got to therefore work out if the ball's going forward, how much momentum is the cannon going to have going backwards. So the momentum of the ball is mass times velocity, 2 times 10, which is 20 kilogram meters per second. That's in the forward direction. The momentum of the cannon is therefore going to have to be 0 minus 20 kilogram meters per second, which gives us minus 20 kilogram meters per second. Okay, and then to find the recoil velocity, we are going to have to take the momentum of the cannon and divide it by the mass of the cannon. So that's 20, or minus 20 if we're being exact, divided by 150, which gives us a velocity of minus 0.13 meters per second. Okay, and the minus shows it's going backwards. Now, that is the rule is the case in a closed system, which means that no external forces are applied. If we have a non-closed or an open system, then an external force might be being applied, and in that case that can cause a change in the overall momentum of the system. Now, we already know that F equals ma, force is mass times acceleration, and we know that acceleration can be calculated as the change in velocity, v minus u, divided by t. So if we put those two equations together, we get F equals m v minus u over t, or F equals mv minus mu, divided by t. Now, mv and mu represent the start and the end momentums. So force is equal to the change in momentum divided by the time taken for that change in momentum. So here's a couple of questions for you to have a go at. Please do have a go at them, pause the video while you're doing them, and then I will go through the answers. Okay, so we've got a car of mass 600 kilograms travelling at 30 meters per second, and it drives into a wall. If it doesn't have a crumple zone, that's the part at the front of the car that squishes up when it collides. It takes 0.5 seconds to come to a complete stop. What force is applied? So we're using force equals change in momentum divided by time taken. Okay, so the change in momentum, we've got 600 times 30 as the initial momentum, and the end momentum, it's come to a complete stop, so that's 0, and that's going to be divided by 0.5. So if I pop that into my calculator, I've got, first of all, the top is 18,000 divided by 0.5, and that gives me 36,000 newtons of force. Okay, so there's a lot of force being applied there. Part B, if it has a crumple zone, it takes only 2 seconds to come to a complete stop. So what force is applied then? So again, the change in momentum is 600 times 30 minus 0, but this time we're divided by 2. So again, it's 18,000 but divided by 2, which gives us 9,000 newtons. So what you can see there is that by increasing the time taken, we've reduced the amount of force acting on the passengers, which therefore makes it much safer for the passenger. Okay, and this is a key idea when we're looking at momentum and we're looking at car safety and other safety features, is that idea that if you increase the time taken for a collision, it reduces the force applied and therefore reduces the danger to the person. Okay, so a common type of question, why do cars have crumple zones? You get these 4 points. The crumple zone increases the time taken for the collision. The change in momentum stays the same. The rate of change of momentum is reduced, therefore the force applied to the passenger decreases. Now that's the same for lots of other features. So if I say, why do cars have seatbelts? The seatbelt increases the time taken for the collision. The change of momentum stays the same. The rate of change of momentum is reduced. The force on the passengers decreases. Or it could be for crash helmets. Again, increase the time for collision. Spongy bits on the playground floor. Increase the time taken for the collision. Anything where you're talking about something that is cushioning something else, you can use those 4 points to explain how it works. Okay, have a go at some PEQs.